Page 15 of Applications of Calculus. So for the first problem, we're going to be continuing on with integrals to find areas under curves. Still, we are doing the area between this curve and the x-axis and some horizontal boundaries. Just to see what this looks like, let's graph it in the calculator. So I typed in the function and then I'm just going to graph it. So do you see how it like crosses the x-axis slightly to the right of the origin? So basically it's going to be kind of like this, and then the right edge is going to be x equals 4. So it'll be kind of like that. So we kind of need this intersection point here. How do we find the intersection point? Second calc 0. Second calc 0 finds the intersection points with the x-axis, also known as the x-intercepts. So one tricky thing is when you turn on second calc 0 or other things that have left boundary, right boundary, it puts the cursor at x equals 0, and notice that this function has no x equals 0. So you need to first move the cursor slightly to the right so that it'll start appearing. So that's kind of a pegadinha. I'm going to put the cursor slightly to the left of the x-intercept, which is right there. I hit enter. Then I move it slightly to the right of the x-intercept. I hit enter, and then I press guess. And so the 0 is 0.25 comma 0. So this x value here is 0.25. We could have found that by setting y equal to 0 and doing a little bit of algebra. We could have found that x equals 0.25. All right. All right, so now we're going to set the integral. We're going to integrate from 0.25 to 4. And we're going to put the function 2 minus 1 over square root of x inside. And then we're going to put dx. And we're just going to integrate this inside function. We're going to rewrite 1 over square root of x as x to the negative 1/2, okay? So it would be 2 minus x to the negative 1/2. When we integrate 2 minus x to the negative 1/2, we are going to write 2x minus, we're going to raise negative 1/2 by 1. So negative 1/2 plus 1, or negative 0.5 plus 1 is 0.5 or 1/2. So it would be x to the 1/2. And then we put 1/2 underneath because that's how we do integral power rule, right? And then we have a bracket and 0.25 and 4. So remember that 1/2 underneath is the same thing as multiplying by 2 on top. So I'm just going to rewrite this a little bit. 2x to the 1/2. And of course 0.25 to the 4. So we're going to put 4 into the x's. We're going to put 0.25 into the x's and subtract the results. So the first one is going to be 2 times 4 minus 2 times 4 to the 1/2 minus, and then we're going to have 2 times 0.25, which is also known as 1/4, minus 2 times 1/4 to the 1/2. Okay, so this would be 2 times 4 is 8. 4 to the 1/2 is 2. 2 times 2 is 4. So 8 minus 4 minus 2 times 1/4 is 0.5. 1/4 to the 1/2 power. What number do you multiply times itself to get 1/4? It would be 1/2. So minus 2 times 1/2. 2 times 1/2. So that would be the same as 1. So 8 minus 4 is 4. Minus 0.5 minus 1 is negative 0.5. So that would be 4 plus 0.5, right? 4 plus 0.5, which is 4.5. Number 3, find the area enclosed by one arch of the curve y equals cosine 3x and the x-axis. Okay, so what does cosine 3x looks like? Well, it pretty much looks like regular cosine. But it's got this 3 here. It's a horizontal compression by a factor of 3. So instead of going from 0 to 2 pi, it goes from 0 to 2/3 pi. Okay, which means that this would be 2/6 pi, or 1/3 pi. And this would be 1/6 pi. Okay, and so we want to know what is the area enclosed by one arch. So that would be this area here. So it would be between negative pi over 6 and pi over 6. And of course the x-axis. So let's write that out. It would be negative pi over 6 to pi over 6. Function would be cosine 3x. Cosine 3x dx. Let's take the integral. The integral of cosine 3x would be sine 3x divided by 3. The divided by 3 is to cancel out the chain rule. I'm going to show you that that's true by taking the derivative of sine 3x over 3. The derivative of sine 3x over 3 would be cosine 3x over 3, and then I would do chain rule of the inside, so that would be 3, and the 3's would cancel out, and oh yeah, it worked. Okay. You don't have to be good at integrals, just be good at derivatives. So we are going to substitute in pi over 6 and negative pi over 6 and subtract the result. So that would be sine of 3 pi over 6 divided by 3 minus sine of 3 pi over negative pi over 6 divided by 3. So what is 3 times pi over 6? It would be pi over 2. What is the sine of pi over 2? The sine of pi over 2 is the sine of 90 degrees, which is 1. So 1/3. Minus, what is the sine of negative pi over 2? That would be negative 90 degrees, which would be negative 1. So 1/3 plus 1/3 is equal to 2/3. So the answer is 2/3. That wasn't so bad. Number 4, write down an expression for the area of each region described by the following boundaries. Use technology to calculate the area. Okay. So it is, oops. Let me draw that, and then I'll draw natural log of x. Looks like that. So we want the area between x equals 1. Remember, x equals 1 is right there where it has an x-intercept, and 4. And of course the x-axis. We want this area here. How do we write that in an integral? We write the integral from 1 through 4 of natural log of x. We're going to find the integral of natural log of x. Now, be careful. We know the derivative of natural log of x is 1 over x, but we don't know the integral of natural log of x. We cannot integrate natural log of x. So what we can do is we can evaluate this on the calculator. Okay, so there's 2 ways of doing that. One is we're going to use, you could use the math function and do this, fn int. Okay, and then, oops, I did it in the wrong screen. Get out of there. Okay, now you're going to go to math, and then you're going to go to fint. And then you could just type everything in. Let's try that. So we'll put 1 here. We'll put 4 here. We're going to put the natural log function inside with x. Close parentheses. Notice the parentheses are already there. They're just to set off the integral notation from the inside of the integral notation. And then x. Enter. The answer is 2.545. So it would be 2.55. So the answer is 2.55. How could you do this in a more graphical way? We could go to y equals, and then I could put the inside function, which is natural log of x, inside. And then I could graph it. It looks just like what I drew, right? And then I'm going to integrate from 1 through 4. How do I do that? I do second, calc, integral, which is number 7. And then I type in lower limit 1, enter. Upper limit 4, enter. And then it colors it in. How nice. Just like I did there. The answer is 2.55. Okay, so those are 2 ways to do it. Do it the way that you prefer. Now we're going to do the other one, which is y equals x squared e to the negative x. and between 0 and 2.8. So let's do it this way, because I want to see what this function looks like. X squared e to the negative x graph, and I'm going to integrate from 0 to 2.8, and we'll see what that looks like. Integrate, which would be second, calc, integrate number 7, and I'm going to put in 0 to 2.8. 2.8. Okay, and the answer is 1.06. So the integral from 0 to 2.8 of x squared e to the negative x dx is equal to 1.06. Okay, 19b. So up until now, you can see that we've always been doing the area between a function bounding the top and a straight line at the x-axis, which is bounding the bottom. And now what we're going to do is we're going to do something more complicated. We're going to have a function on top and a function on the bottom. So a rounded top and a rounded bottom. Okay, so write two integral expressions to calculate the area between the two curves. One using f of x and gx, and the other using yu and yl. So notice that we call this top function f of x or y subscript u, and the bottom function is called g of x or y subscript l. So let's see, with f of x and g of x, you would write integral from a to b of f of x minus g of x. F of x minus g of x. Okay. Before, we only had f of x, and the bottom was the x-axis, which is basically y equals 0, right? Now we are actually going to subtract a different function, which is g of x. So like f of x minus g of x will calculate this little sliver here, this height minus this height. It'll give you the length of this little sliver, right? And then you would multiply the sliver times the width dx, and that would give you this little rectangle, and then you would repeatedly do that of all these little rectangles, and you'd add all the rectangles together, and it will give you the area of this curved space. Okay, so this would be the expression for f of x and g of x. If I wanted to write a similar expression using y's, I would put y subscript u and y subscript l instead, like so. Okay, all right, and write an integral expression that calculates the area between curves f of x and g of x that works even if f of x is only sometimes greater than g of x. Did you notice that like we cleverly, strategically did this integral between a and b is exactly where the curves cross each other? And if we went past here or past here, we would have a problem, because instead of f of x being on top, g of x would be on top, and that would make the little sliver f of x minus g of x, it would make it negative, because if g of x was on top, then g of x would be a number that would be bigger than f of x, and then the result would be negative. So that would be kind of a mess, right? Now, on the calculator, you can still do that kind of problem without you could find the area, and you don't need to worry about which one's on top by using absolute value. So you could do integral of like, you know, the two limits, and then you would put the absolute value of the inside. So you could do like f of x minus g of x, and if we have the absolute value here, then you don't really need to worry about which one's on top. Okay, and then it would add up all the areas as positive areas. So like we could actually, like, what if you wanted to like say, okay, besides this area here inside, I would like to add up this area and this area too, and I don't want them to be negative just because the f and the g flip positions. I want them to be counted as positive. So by doing this absolute value, it'll do that. Anything within a and b, doesn't matter if f is on top, g is on top, it'll always assume that the area is positive, and it'll add it all together. So let's do number 1 here. Find the exact value of the area bounded by these two functions. I'm just going to graph this really quick to show you what it's going to look like. I'm going to program in y1 this function here. So I'm going to put x squared plus x minus 2. And I'm going to graph it. So you know that x squared plus x minus 2 has an a value that's positive, so it opens up. And you know if you factor it that it's going to cross at -2 and 1. So look at this. They want the value between the x-axis and x squared plus x minus 2. This is a little different than the other ones, right? Because this area is below the x-axis. When you integrate an area that's below the x-axis, are you going to get a positive or a negative number? You're going to get a negative number, right? So when you get this negative number, they want a positive number because they say find the exact value of the area bounded by blah, blah, blah. Areas in general are positive. I mean, you can do an integral. This integral of this area would be a negative number, and that's fine. What's the integral of this? It's negative. But when they ask for an area, normally they want that to be positive. So how do we make this come out to be positive? What we do is we define another function, which would be y equals 0. And then we just pretend, just like we did here, we have a function on top and we have a function on the bottom, and we subtract top function minus the bottom function. Now in this case, the top function is y equals 0 and the bottom function is the blue function. So why don't we do that? So the blue function and the red function. The red function is y equals 0, right? So let's make a integral which will do red function minus blue function. We'll do the integral from, and we can look on the graph and we can see that the intersection points are -2 and 1. And we're going to put the red function minus the blue function. So the blue function is x squared plus x minus 2. Be very careful to put it in parentheses so that the negative sign will distribute. Now we're going to distribute the negative sign, so we'll have -2 to 1, negative x squared minus x plus 2 dx. Now we're going to do the integral of the inside. It'll be negative x cubed over 3 minus x squared over 2 plus 2x bracket -2 to 1. Then we're going to substitute the 1 in for the x's. We're going to put the new -2 in for the x's, and then we're going to subtract the results. So let's try to do that. So in the first one, we're going to put -1/3 because we put the 1 into the x cubed over 3rd. We're going to put -1/2 because we put the 1 into the x squared. And then finally, plus 2. And then we're going to do the same thing with the -2. We're going to put -2 in for x cubed. That gives us -8/3. Oops, that could be positive because, oh, this negative is actually, it needs to be here, doesn't it? Negative, this negative is here. This negative comes from putting -2 into x cubed, right? Okay, so be careful with that, sorry. If I put -2 into x squared, -2 times -2 is 4, so it's just 4 over 2. And if I put -2 into 2x, it would be -4. Okay, so now let's be careful with the negative signs. -1/3 plus -1/2 is equal to negative, let's see, that would be 2/6 and 3/6. That would be 5/6. -5/6 plus 2. And then minus, and then minus -8/8 would be positive 8/3. Minus 4/2 would be -2, and -4 is -4. Okay. Okay, so let's see. The first one would have -5/6 plus 2. And then I'm going to distribute the negative sign among these three, so I'm going to have -8/3 plus 2 and plus 4. So 2 plus 2 plus 4 is 8. Let's see, if I change -8/3 to 6, it would be -16/6. -16/6 minus 5/6 would be -21/6. This would be 8 minus, and let's 21.6 is the same thing as negative, let's see, how many times does 6 divide into 21? 3. So it would be negative 3. That would be 18.6. And then there's left over negative 3.6. So I would put negative 3 minus 3.6. 3.6 is the same thing as 1/2. So we have 5 minus 1/2, which is equal to 4.5. Yuck. Okay. Last one. The x-axis and the part of y equals 3x squared minus 8x plus 4 below the x-axis. Okay, so this is a very similar problem. Okay, we're going to have this is a parabola which goes below the x-axis, and we just want to calculate this area that's below the x-axis. We're going to do a similar thing here. We're going to integrate between two limits, and we're going to do 0, which is the x-axis, minus this function 3x squared minus 8x plus 4. We could use quadratic formula or something to figure out what the x-intercepts are. Why don't we just use the calculator for now? Who wants to go factoring this thing or doing quadratic formula when the a value is 3? Not me. So 3x squared, So let's just figure out what these x-intercepts are. 3x squared minus 8x plus 4. Graph. Okay, we can't really see, so let's do second calc 0, which is number 2. Enter. Enter. Guess. And it's 2/3. So one of the x values is 2/3. And the second one over here looks like it's 1. Let's just make sure second calc 0, which is number 2. Move the cursor here. Enter. Move the cursor to the right. Enter. Guess, enter. 2. Oh, it's 2. Sorry, not 1. Okay, so we're going to replace a and b with our real limits, which are 2/3 and 2. And then we're going to integrate that. We're going to distribute the negative sign. Let's rewrite it first with the negative sign. So we're going to have integral of 2/3 to 2, negative 3x squared plus 8x minus 4 dx. And when we integrate this, we'll get negative 3x cubed over 3 plus 8x squared over 2 minus 4x bracket 2/3 to 2. X cubed. And this would be 4. So this is equal to negative x cubed plus 4x squared minus 4x, and then we just plug in 2 and 2/3 and subtract the results, and oh my god, that's terrible. Let's do this with the calculator. Second calc. Now when we do this with the calculator, we're going to get a negative number because this is below water, right? So, oops, second calc integral, and then we'll do lower limit of 2/3, 2 divided by 3, enter, and the upper limit will be 2, enter. And the answer is, negative 1.185. But when we do 0 minus that, it's going to make it positive. Okay, so to do this analytically, we would substitute 2 in for all the x's, we would substitute 2/3 for all the x's, and we would subtract the 2. Okay, all right.